Everyone. So this next lecture is going to be based on Steck 9.3, which is on logic gates, and I'll wrap up chapter 9. And so previously, right, in 9.1 and 9.2, we talked about binary logic and how we actually represent values in binary numbers. And we'll also talk about 2's complement, and that's the way we actually can store information so that it follows the same algebra. Well, it follows the same method of adding and subtracting, right, as what we learned in decimal. And that's why we have to use the 2's complement to represent the negative number. We don't end up with two negative zeros. So now we're going to see how these numbers are actually physically manifested on your circuit. Okay, so we're going to talk about logic gates. So the first one we're going to talk about is going to be the boring one, as usual. Is the buffer gate. What the buffer gate does is that whatever your input is, the output is the same. Okay, so the gate is usually represented by this little triangle. There'll be different shapes for different gates. So in this case, the logic gate is just a triangle. Okay, and what happens is that whatever A is, Q just follows. Okay, and this little table here on the right is known as the truth table. And basically, this is how it's a little dictionary on how the inputs and outputs are related to each other. So the inputs are represented by letters that are in the beginning of the alphabet, so A, B, C, D, E, F, G, right? And then the outputs are represented by the later Q, R, S, T alphabets instead. Okay. So the book doesn't show you this, but basically, as I said, whatever output is, it follows A. So basically, the circuit that makes this is basically a transistor and one resistor. So you can make this very small, very cheap, right? So as you remember from chapter 4, right, this is actually the emitter follower circuit. Okay, right? Because whatever Vin is, V out is going to be the same, right? And then what happened is that if you make this resistor here big enough, what happened is that it basically will either swing to VCC or swing to 0, depending on whether or not the transistor is on or off, right? When the transistor is on, right, you drive some amount of current through this, a large amount of current through this from VCC, and basically this creates a large delta V between this resistor, right? And that gives you a high V out, basically approximately VCC. It's actually probably going to be VCC minus 0.2 volts because of this transistor. But when it's off, right, there's no current going through this resistor, and the change in voltage across the resistor with no current is 0. And since you have ground here, basically what happens is that VCC V out becomes basically approximately 0. Oops. Right. Okay. When Vin is high, right, or 1, right, when Vin is low or 0, right? Right. And then 1 and 0 doesn't necessarily mean 1 volt, 0 volt, right? 1 in TTL means 5 volt, 0 in TTL means 0 volt, right? And that's what's going to determine your states. Okay, let's do a little something less boring, but still pretty simple. So it's nice that the book starts you off with something pretty simple. Okay, and that's the inverter gate or the NOT gate. The diagram is very similar, but pure little circle at the end of it. So this little circle always means opposite. Okay, O for opposite, I guess. So what it does is that the truth table, right, we're going to be playing around with these truth tables a lot in the pre-lab, right? Whatever A is, Q is the opposite. Okay, it's just a very annoying kid or something like that who always wants to say the opposite of what you're trying to tell them to do, the opposite of what you tell them to do. Okay, so if A is 1, output is 0. If the input is 0, the output is 1. Okay, it's just always opposite. Okay, and once again, this is made by just a single transistor. Okay, but instead of having the resistor and the output at the emitter part of the transistor, right, you put it at the collector, right, because this will get an opposite, okay? So this is all known as the inverting amplifier, right? Inverting amplifier, right? And the amplification is basically R over Ri here, but if you just remove this Ri, so make Ri equal to 0, you get technically infinite gain, but you know that the gain is going to be railed against your voltage supply, in this case 5 volts, okay? So that's why it gives you the opposite. So whenever A is at 5 volt, the V out is going to be 0. Whenever V in is 0, is the input, the output is going to be at 5 volts. Okay. So notice that we start using the symbol A bar, right, to represent the opposite. If you noticed it, I didn't point it out yet. This is known as the propositional logic symbols. And there's a little table here from Wikipedia, and we're going to use this a lot. So if you're not familiar with it, I suggest you look at this and maybe even have it handy sometimes just to look things up. So the not thing we were talking about, right, is this A bar. Okay. Another way to represent not is also with this little tilde, this saying, oh, I want the opposite, or with a -1 sign or negative sign. Depending on where you see the symbol, it means the same thing, but so if you were doing this on a certain circuit board or a certain system, only one of those symbols work, unfortunately. Okay, so you have to know all three, well, technically all four, if you were to do things in a lot of different places. But these little signal down symbols, we don't use that a lot, at least not in this class. Especially the book used mostly these three. Okay, so make sure you know these three, and then when we get to the ands, I'll describe which one is the one that the book actually uses. Okay, so those are the one input gates. We're going to do two inputs now, right? You can only do so much in binary numbers with one input. Two inputs, right? We're going to start with an AND gate. An AND gate basically kind of does what it kind of sounds like, right? If A and B are high, your output is high. Okay, if A is high, B is low, your output is low. If A is low, B is high, output is still low. If both are low, then you go low. So on an AND gate, the output is only high when both of the inputs are high. Okay? Okay. And this Q here is the output, right? And it's symbolized with A dot B, or A, next to B. Let's not worry about this caret one for now, okay? Because we don't actually use it in this book. So why is it represented by a dot, right? Because typically, right, a dot in math represents multiplication. But an AND gate is actually the same logic as multiplication. And we can show you why, right? Because, right, let's just, right, 1 times 1, right, which is, in this case, A and B, right? 1 times 1, that's the only time you get 1 as the output, right? Because if either A is 0, right, even if B is 1, you still get 0. If B is 0, A is 1, right? 1 times 0 is still 0. And of course, 0 times 0 is always going to be 0, right? So basically an AND, right, it's the same logic operation as multiplication in binary. Okay, so this is something that to make sure you don't mix up, because you would think AND is like, oh, you're adding things together, but it's not. It's actually the OR gate that adds. Right, so the circuit that makes this work is, since you have two inputs, you're going to have two transistors linked on top of each other. So these are the two inputs, A and B, and there's some resistance to them already. Okay, and the output is taken at the second transistor's emitter. The reason this gives you the AND operation, right? In order for current to flow through, right, from the VCC, let's call it VCC as opposed to 6 volt, right? This has both of these transistor has to be on, so that means both of these input has to be high in order for the out for current to flow through. If current flow through, right, that means then this output is going to be high. If no current flows through, right, that means it's going to be tied to ground, because no current means no voltage drop across this resistor. Then you get 0, right? Okay, right, and that's how physically an AND gate work inside. Okay, we can put a NOT in front of it, meaning you do the AND and then you flip the output. Okay, so what a NOT gate does, right? Let's just go up here, right? It does the same thing. So these inputs are the same. You notice that 1 1 1 0 0 1 1 1. Sorry, 0 0. Right? Whatever the output is, it's just gonna, the NOT just gives you the opposite, right? If it gets you, if you have a 1, it gives you a 0. If you have 0, it gives you a 1 instead. Okay, I'll just go with this. Okay, all right. And this is known as NAND gate because you're combining a NOT and an AND together. And this is actually one of the most useful gate, and it's actually known as a universal gate because it allows you to build anything out of this. Okay. Some of you guys might have heard like NAND flash drives, and that's why these are actually used for that. Okay. Okay. So how does a NAND gate, right, gets built with transistors? It's very similar to what you have up here, but instead of taking the output beneath the emitter, you take it above the collector of the transistors, so you have the opposite, basically. Okay. Right. Hopefully that makes sense. Okay. The other gates that you'll see is actually OR or NOR. Okay. So an OR gate basically adds two numbers together, which is not exactly that. We're going to see an exclusive OR, and that's actually going to be the actual best plus symbol that we can use. But the truth table is that, well, if A and B are both high, an OR gate basically gives you high, because it only cares if one of the input is high. Okay, if both of them is high, okay, fine, you know, whatever, whatever. It just does the gives you a high also. So if A or B is high, it gives you 1 as the output. If neither is high, that's the only case it gives you 0. Okay. Okay. In this case, it gives you a is represented by a plus, which, you know, I don't especially like, but you know, that's the way it was developed. Okay. A NOR gate. So this is the NOR. Oh, this is an OR gate. So OR gate, basically what happens is that it takes the output from both of the transistor, and that way if even one of the transistor turns on, then you have current flowing through it, and therefore it gives you a current across this resistor once again, right? And that way it gives you a high output. Okay. So this is an OR gate transistor set of transistors. Okay. And just like the case of the NAND versus AND, you also have a NOR gate. The NOR gate is very similar, but whatever the output is, you just get the opposite. Okay, so hopefully, and these are going to be the NORs, and you're going to find that the NORs and the NANDs are actually more useful than the ANDs and the ORs. Okay. As I mentioned before, there's also what's known as an exclusive OR gate. Okay. Oh, let me just make sure that the symbols are nice. Okay. So the symbol for an OR is basically kind of this kind of like little spaceship shape, right? And that's the symbol for an OR gate. And then if you want a NOR, you put a little circle at the end of it. Okay. And I think I also forgot to tell you about the shape of the gates for an AND. And it's basically kind of this flat version. So this difference between the OR, right, is that you don't have this curved line here. You have a flat line here instead. That represents an AND. Okay, and then the NAND, of course, is going to be this flat part with a little circle on top. Okay, it's like a little, you know, hat shape. Okay. Okay, an XOR gate, right? It looks similar to the OR gate, but then you put a second um, uh, parentheses or curved line in front of the input. Okay. Sometimes the line will go through here, sometimes it doesn't. It's the same symbol, it doesn't make any difference. Okay. In the logic representation, right, it's represented by this plus with a circle around it, just to say that it's exclusive. It's like, oh, you have to be in the circle. Okay. The only difference between the OR and the exclusive OR is that 1 gives you a 0. Okay, that's the only difference. Okay, so it's only high if only one of the inputs are high. Okay, and that's going to be actually the other. Oh, I think the exclusive NOR is the other universal gate. Okay, anyway, so that's what the symbol looks like. Okay, so you have this little bullet thing, or the shape tip of the rocket shape with like 2 curves instead of 1. That changes forward to an exclusive OR or a XOR gate, let's say. Okay, there's also the exclusive NOR gate, so which is, you know, the same thing as up here, but then you do the opposite once again, right? Right, it's the NOT version of it. So the way you symbolize that is you put the exclusive OR, but then you put a circle in front, and now it's the XNOR gate. Okay. So these are all 2 input gates, and these are all the logic you need in order to do a lot of computation. In fact, the only things you actually need is either a NAND. A NAND is actually a universal gate, and an exclusive NOR gate is also a universal gate. You can build anything out of that. Okay. So let's do a quick example and see how these gates, right, gets coupled together if you were to change some stuff around, and how would you build something like this. So this first one here, right, is an AND symbol, but then instead of putting the NOT right at the end of it, it puts it at the beginning. Okay, just to trick things up. So what this is actually doing, right, the output is actually, right, whatever A is, right, it actually takes the opposite of it, right? Whatever B is, it takes the opposite of it. And since this is an AND gate, right, you're multiplying these together, and then that's represented by a dot. Okay, so we want the little practice wants you to work out the truth table. So just put TT here, right? So let's see what happens. Okay, so the way you make a truth table is you put A and B here, and you can go straight to Q if you want. But what I'm going to do is I'm going to do A bar, B bar here. Okay, and that way I can keep track of which one I'm doing. Well, I'm doing one step at a time instead. I think if you have enough practice with this, you can just skip to the end, but let's just do it the long way the first time. Okay. Okay. So what this is, right? So we'll always get the opposite. So whenever I see a 1, I put a 0. So I see a 1, I put a 0. I see a 0, I put a 1. I see a 0, I put a 1. I see a 1, I put a 0. I see 2 zeros, I put 2 1s. Okay. And then you want the AND of this. So remember, AND is only high if both inputs are high. That means this is 1 and the rest of these are 0, right? Because those either have 1 or 2 zeros in it. Right, so that's truth table of it. Okay. And the neat thing about this is that, well, is this equivalent to something else? Okay, right? Because hopefully I did it in the same order. Yeah. Okay. So I'm going to go up to and scroll up and see if there's anything that's 0001. Okay. Go up, go up, go up. Right. So look at here. Right. This is the output that we get from that opposite of A and B, then an AND. It's the same thing as the NOR gate. Okay. So basically, right, so if I have A, dot B, right, that's what this symbol represents, is the same thing as A, okay, and the NOR symbol, here's the NOR symbol. NOR symbol, right, is A plus B, and then the whole thing opposite, okay, right, and this is sort of neat, right, so, right, initially I have two inputs with knots on top of them, and an AND, right? If I connect these two bars together, it flips the symbol in the middle, right? From an AND to an OR, okay? So this is, and this is going to turn out to be De Morgan's theorem. Okay, this is the NOR, this is an AND, right? But then the two inputs are opposite, okay? Not to both inputs. Okay, it's different from a NAND gate, right? Because we opposite the input before we put it into the gates, okay? Not after. Okay, so that's sort of neat. Okay, part B, right? Let's do another example. Okay, so in this case, right, Q is going to be, right, the opposite of A plus the opposite of B. So this is the OR symbol. Okay, so I'm going to have the same truth table up top. Okay, in fact, yeah, let's just do it the long way. One more time, okay? So 1, 2, 3, 4 lines. 3 and 4 lines, okay? 4 rows. Okay, A, B, A bar, B bar still, right? Q, right? That's going to be very similar. So just do this a little quicker. I'm just copying what's on top there, literally the first 4 columns. Okay. The only difference, instead of doing an AND here, sorry, doing an AND up here, I'm going to do an OR. Okay. 0 or 0 is 0. 1 or 0 is 1. 1 or 1. 1 or 0 is 1. 1 or, since it's not an exclusive OR, this is also 1. Okay. So what is that equivalent to? If we go back up to here, I want 0, 1, 1, 1, right? Let's see if there's a gate that does 0, 1, 1, 1. So that's the NAND gate. Okay. So basically, right, A bar plus B bar is the same thing as A dot B, the whole thing opposite. Okay. Notice once again, right, if we connect these bars together and flip the type, right, from an OR to an AND, then you get the equivalent. Okay, and this is going to be turned out to be De Morgan's theorem. Okay, and this is going to be true in general for even not just 2 input gates, but 3 or 4 input gates. I'll let you guys. Okay, well let's just do C, since sometimes this gets a little tricky. Okay, C is asking you to make a NOT gate out of a NAND. How we do that? Okay, so remember that the NOT gate is only one input, but a NAND gate, which is this, right, has 2 inputs. There's very limited the options you have, right? Okay, so you have A and B here. Okay, and you could, like, connect the output to the input and stuff like that, but that's gonna be problematic because, right, whatever A is, you don't want that to be Q, you want it to be opposite, right? Oops, I should draw these A and B over here, right? And you only have single thing, so well, maybe the first thing to try, right, is that you make A and B the same, right? So let's say the input is C, and let's see what happens. Okay, so the NAND gate, right, is the AND between them, right, but the opposite. So since C is piped into both A and B, right, if C is equal to 1, then that means A and B is equal to 1. Let's just do the truth table and see what happens. Okay, and then we can compare, right? 1, 2, 3, C, A, B. These a little boring, but we'll see. Okay, so you have two possibility, right? So if C is 1, since they're connected together, this is 1, right? If C is 0, these are connected together. This will give you 0. Okay, and this is a NAND gate. NAND means, right, if there's AND between them, right, an AND will give you 1, but since you want the opposite, since it's a NAND, it gives you 0, right? And in this case, and then for the second row, the 2 is 0, the two inputs are 0, the AND between them is 0, 0 and 0 is 0, right? But you want the opposite of that, so that gives you 1. So this gives you exactly the inverting output that you want for your NOT gate. So if you need a NOT gate, you don't actually need one. You can just use an AND gate and just connect both inputs together, and then you'll get a NOT gate. Okay, and that's how a NAND gate actually can be made into any gate you want, and we can we'll play around with that. Okay. All right, so that's all for chapter 9. And next lecture, we're going to jump to chapter 10 and do some Boolean algebra, and play around with multiple gates, connect them together, and see what we get. Okay. All right. See you next time.